In this video, I'm going to be talking about quantum computing and about the Bell's inequality. This is the most important part in this video we are going to cover in. So let's get started. So let's start off with Bell's inequality. But before that, there's another thing called local realism. So actually, local realism is anything that you ever see in your real life. For example, that humans can't travel faster than light. So actually, no one can travel faster than light. That is the realism. So that is the local. So locality means this. No one can faster than light. And realism is if a tree falls, it makes sounds. Let's imagine you're on a forest and without just a little decoration, imagine there's a tree over here with a few branches on it. And if it is gonna fall, then it will make some sounds. So this is realism. Whether there's a human or not, it will make sound. That is the truth. So that is what local realism means over here. So let's get into the video. So over here, this is what this Bell's inequality is. So as I told in the last segment, Victor sends over here. Okay, let me change the color to white so that it's visible. So Victor sends two particles. So to simple down qubits, actually qubits is a complicated one of the quantum ones and zeros with in a quantum computing. Okay. Likewise, how we have binary digits. Likewise, in quantum computing, we have qubits. So let's see with values 1 and 1 plus 1 and minus 1, plus or minus 1. So he has a capability of sending two numbers, either it's plus 1 or it's minus 1. These are the maximum two values he can send to each person. He can send whether a plus 1 or a minus 1 to each of them. So there are two people, namely Alice and Bob. So they can measure only 1 plus or minus 1, and that's their capability. So this horizontal detector can detect all the plus, and this vertical one can detect all the minus. And likewise for this also, for Bob it is plus and minus. So this is what they can detect. So the possible solutions can be many, like Alice can get X, which she can use a X. So X means in case my plus 1 and minus 1. Let's just remember that here it's plus 1 minus 1. So kind of. So whether now Alice gets is what is. So let's take AX. So AX equals plus 1, and for Bob it's also plus 1. So plus 1 plus plus 1 equals 2. Next, AX and BY. So Alice gets plus 1 and Bob gets Y. So Y is minus 1. Plus 1 minus 1 equals 0. And another one, this all equals 2 plus 0 equals 2. So AYBX, so whether he gets minus 1 plus the x which is plus 1 So actually now here is it is Alice value is y, so -1 plus, and Bob value is x, so -1 plus 1. So -1 plus 1 z is equal to 0 plus or minus. So it's over here is minus, which you can see it over here. So it's minus. So plus 1 is equal to plus, okay, now here it's minus. Let me use minus x. So x value over here, for it's actually ay by, so both of them gets -1. So -1 -1. So -1 equals -2. So the value over here is -2. However, you either get +2 or -2, well, if you add all the statements. Actually, there's a mistake. This shouldn't be there. If you add these two, you will get plus or -2. So the next, if you add this, your answer will be 0. According to Bell's inequality, the answer must be, okay, so let me erase all the. So according to Bell's inequality, the equation which you found should not go more than 2. So according to Bell's inequality, it should be more than 2. Okay, sorry, more than, so it will be more than 2. More than or equal to 2. That's not more than that. So this is always more than 2. So maximum value is 2. Actually, George find it as giving it as 2.8. So that's why he got a Nobel Prize for disproving the Bell's inequality. So let's match it with quantum particles. So this is called as qubits. It doesn't have plus or minus 1. No, it's just a value. So it just goes to Alice first or Bob. It can either travel in both of the directions. So that's it, guys. Thank you for watching. Let me see you in the next video, and bye.